Okay, so this week I chose four problems. One of them is not like the other three because Joanna asked for a knapsack problem. So I pick a knapsack problem, and then the other three are graph problems, but they're all graph problem of the same type. So I don't know how many people tried. I see Blake tried D. Am I gonna guess that you just submitted whatever was the solution for the UVA version of this problem, and then it didn't pass? It's Blake here. Okay, but anyway, if this problem D is actually one of the problem that I used as an assignment problem in 3200. It was actually on a different online judge, and it was recently ported over to Caddis. But when they ported it over, they changed the input format a little bit. So I actually didn't even bother reading the problem at first, and I just submitted whatever I had for that online judge over here, and immediately got runtime error. And then I have to look at what's going on, and then I realized they had to change the input format, even though the problem, of course, is pretty much exactly the same. So anyway, so let's get started. So 9 packs. This is problem is about how you can buy hot dogs in packages of 10 hot dogs and buns, hot dog buns. You can buy them in packages of 8. So when you buy 1 pack of each, you get 2 extra hot dogs, and then it's kind of a mess to try to figure out how many packs you need to buy of each so that you don't have any leftover buns or leftover hot dogs. And so, for example, they say 4 packs of 10 hot dogs, 5 packs of 8 buns will give you 40 each. But you can also do it in fewer packs if you buy 2 packs of 10. And then if you can buy 1 pack of 8 buns and 1 pack of 12, and so on. So for this problem, you'll determine the fewest packs you need to buy to make hot dogs and buns come out even, given a selection of different bun and hot dog packs available for purchase. Okay, so let's look at the input. You have an integer h, which is the number of different types of hot dog packs available. Then followed by h integers, little h1 up to hh, which is the number of hot dogs in each pack. Then the next integer is capital B, which is the number of bun packs available, and then all the different sizes that they have, and then the values h and b are between 0 and 100. So you cannot have more than 100 different packages. And then the sizes of the packs are between 1 and 1,000. Every available pack is listed individually. So if there were 5 8-bun packs available, then the list of bun packs would contain 5 copies of the number 8. Okay, so that's the setup. If it's not possible to purchase an equal number of 1 or more hot dogs and buns, output possible. Otherwise, output the smallest number of total packs you can buy, counting both hot dogs and buns, to get exactly the same number of hot dogs and buns. Okay, so basically, if you think about only hot dogs or only buns, so think about just one thing at a time, then you're basically doing a kind of a knapsack or coin changing problem where you have a bunch of different denomination. Okay, let's see. I need to start my whiteboard application. Okay, so you have, let's say, 4 packs. Uh-oh. Shoot. This is not good. My pen is not working. And that whenever my pen doesn't work, my desktop usually crashes pretty quickly. Okay, so what am I going to do? Okay, let me attempt to do the universal fix for everything, which is to unplug and plug in something. And if I crash, then I will try to restart my Zoom meeting. Okay. Now I unplug and plug. Okay, now my pen works. Now I start my whiteboard again and hope that I don't crash. Okay, so you have the hot dog packages. So H packages, H1, H2, up to HH. And basically you want to know how many hot dogs you can buy. Okay, so what are the different hot dogs you can buy? Well, you can buy H1 with one package, H2 with one package, and so on. You can also buy H1 plus H2, H1 plus H3, and so on and so forth. And then also for each value, you can buy what is the smallest number of packages needed. Okay, so this is actually a very common coin changing problem in some way. If these are your coin denominations and you're asking what values can you make, and for those values that you can make, what is the smallest number of coins you need to make it? So the standard way of doing it is just doing something like this. So f of some value v, and well, okay, which index do I want? It doesn't really matter. K will be equals to the smallest number of packages needed to buy V hot dogs using H. Okay, maybe just to make things simpler for coding, I'm going to make things zero based, and then I'm going to say using H0 ... up to HK. Okay, so oh, actually, what should I do? Should I? Okay, let me think here. Okay, maybe I'll stick with the one base. I don't remember exactly what I did with my code, but it doesn't. I guess it's a matter of fixing your notation. Okay, using H1 ... HK. Okay, so basically, I want the smallest number of packages needed to buy V hot dogs. And then if it is not possible, then I need to assign to this a value that is clearly invalid for the smallest number. So I can use -1, I can use infinity, maybe I'll use infinity. Okay, of course, infinity doesn't really exist, so you have to figure out what infinity really means, what you use to represent infinity in your code. So this is a very classic coin changing knapsack type of problem. So then you say, okay, how do you compute this? VK. So V0, so if you're not allowed to use any hot dog packages, then the answer is 0 if V is exactly 0. So if you are not allowed to use any packages, then of course you can buy 0 hot dog with 0 packages. But if V is greater than 0, then there's no way you can buy. Otherwise, so if K is bigger than 0, what is this? Okay. Let me put it this way. So if I'm allowed to use H1, H2, up to HK, then what I'm going to say is I can either buy the last package or don't buy the last package. So if I don't buy the last package, then I need to make the same number of hot dogs with the K-1 packages as before. Or if I use this package, then I need to make V minus HK hot dogs. Okay, K minus 1. So I buy this last package so I don't have to make as many, I don't have to get as many hot dogs with the previous K minus 1 packages. And the fact that I use this package means that I need to add 1 to it. And these are the only two choices. Either I use the last package, I don't. So I take the minimum of these two. And that's my answer. Now there's always some trickiness here. This is not valid. This is only valid if V minus HK is greater than or equal to 0, right? So if you're trying to make 5 hot dogs and you have a package of 10, you just can't use it. So only look at this term if you can actually use that package. And that's basically it, right? So this is a dynamic programming version of the recurrence for computing the smallest number of packages you need to make a certain sum. And if you make the table, so this is F, and this direction is V, and this direction is K, then the base case basically tells you, right? So this is the base case, so 0 here, and then infinity everywhere. And then each of these recurrence for any particular VK, you're going to look at the previous column, K minus 1, either this value, VK minus 1, or a value up here, which is V minus HK, K minus 1, like this. Okay? So if you're building this table and you're just making sure that you compute this one column at a time in increasing K, then every time you need to compute the value, whatever you need has already been computed. Okay, any questions about this part? This will tell you for each value of for each number of hot dogs, whether you can make it at all, and if you can make it, what is the smallest number of packages you need? Does that make sense? Okay, no questions. So I'll put F sub H here to say that this is basically the formula for hot dogs.
So is V the number of like each individual package, or is that
No.
the running total?
The V is the total number of hot dogs that you want to buy.
Okay.
And K is how many packages you're allowed to use, which packages you're allowed to use.
Okay.
So FVK is the smallest number of packages needed to buy V hot dogs using the first K packages.
Right.
Okay, so now there's nothing special about hot dogs. The formula for buns is exactly the same, except that all the H becomes B. Okay, so FB V0, it's either equal to 0 or infinity, if V is equal to 0, if V is greater than 0, and then F for buns, again, this is exactly the same definition. The number of packages you need to buy V buns with the first K packages, so and the formula is exactly the same. Like this. And again, it's only valid if this thing is only valid if V minus BK is greater than or equal to 0. Okay, so basically we're doing this coin changing or knapsack problem twice. One for buns and one for hot dogs. So why are we doing this? We're trying to buy an equal number of hot dogs and buns, not bus. Okay, so what is this equal number? I don't know. Let's try them. Try the equal number from V equals to 1, 2, 3, and there's some upper bound because they tell you that they're at most, I think, 100 packages, and each package is the most 1,000. So if I remember correctly, is at most this much. Okay, so it's like 100,000, which is not that much. Try each of them. For each one, you ask, can you buy exactly V hot dogs? So how do you ask that question? Well, you look at f of h, v, comma, h, using all of the packages. Is it infinity? Okay, because if it's infinity, then you can't do it. If it's not infinity, you can't do it. You can't do it. So you want to do that. Then for the same v, you ask, can you buy exactly v buns? And again, you ask, is this not infinity? Okay, if you can buy exactly v hot dogs and v buns, well then this value is going to give you the smallest number of packages you need. This value is going to give you the smallest packages you need. So you want to compute the number of packages you need to make equal number of hot dogs and buns, no, not H, sorry, it's capital B, would be exactly this. But you don't know whether it's better to try to make 1, 2, 3 hot dogs and so on. So you're going to minimize all of these from V from 1 to up to 100,000 10 to the 5 of this expression. And you don't even care if you can't make it. So if one of these is infinity, well, if one of these is infinity, then when you take the minimum, it should be automatically removed because you never consider infinity as a minimum. And that's the answer. And once you've computed all these values, and this is just a loop of 100,000 steps, because you can read off these values very quickly just from the table. And when you compute this table, you have to compute this table. There are on this side, on this range, there's like 100, and on this range there's 100,000, 10 to the 5 at most. So altogether is 10 to the 7 or 10 million. So you compute, it will take you about 10 million steps to compute the table. You have to do it twice because one for hot dog and one for buns. So it's about 20 million, which is not that bad. So that's basically the solution. Before I show you the code, do you have any questions? Okay, so let me show you my code. Okay, so so I read in the different packages of hot dogs. I read in the different packages of buns. Then I have this array, which is my knapsack array. Now, the way that I show you the function here, I have a two-dimensional function. But if you think about it this way, I start with this row, and then every row, I only need the previous row to compute. So as soon as I finish computing this row, I no longer need to know this row. I can start working on this. I can erase this row. So I really, if I want to save space, I don't actually need to keep this two-dimensional array around. I can just keep one column at a time. And that's what my code does. So okay, I guess I didn't use infinity. I used -1. But anyway, it doesn't matter. So then basically this, it's basically the same way that I was talking about. So I go through all the different packages. Then for each package, I would look at the values. I would try to compute the values. Okay, so let me try to explain what's going on here. So I is equals to the package, which package I'm allowed to be using. So I'm considering each package from start to finish. Then I'm going to, at the beginning, say, this is my knapsack column. This is my value of V here, 0 up to some maximum. So at the beginning, you can use 0 package to form 0, and then -1 or infinity for everything else. Okay, so I use -1 instead of infinity because I guess there's no infinity here. Anyway, forget about this total and so on for now. Then what I'm saying is, for each value, so for each value, I'm going to compute f of I v. Okay, v is actually my j here. So f of ij, I guess in my previous slides I used this. So actually, I guess if I use the same order as I did in my slides, my drawing before, it would be f of j and then I, like this. So j is the value in my code, and I is the package that I'm looking at. So then I said basically that this is the minimum of either f of k minus 1 or f of v minus the package h k minus 1. Okay, so I have this array here. I only have one array, but imagine that I have another copy here. And I want to update this array with one more. Okay, so now I want to consider using package I. So before I didn't have package I. So up to here, I have using packages 1 to I minus 1. And now I want to add one more package. So what do I do? Well, this is the formula. So if I'm trying to compute this entry, so V is here, I try to compute this entry. Well, either it's this entry here, because it's V with k minus 1, or it's, if I subtract V minus hk, it's this entry, sorry, it's 1 plus 1. So it's either this entry or this entry plus 1. Okay, so, but I'm not actually using 2 arrays here. I'm actually just using one array. Why? Because this entry, if it's the same array, it just means I don't change it, because this entry and this entry are the same if it's the same array. The only time I might have to change is if this entry plus 1 is less than what's already here. And that's basically what I do. I look at this entry plus 1, and then if it's less than what's already here, then I replace it. Now, there's a little bit trickiness here, because I use -1 as infinity. I basically have to say, well, if what I already have there is less than 0, that means it's -1, so it's kind of like infinity, or the value is less than what's already in here. Okay, so that's a little bit of trickiness. And then also the other thing is, I also check that this value here, it's not -1, because if it's -1, then I cannot use it, because I cannot actually make the sum with one fewer package. So this is a little bit of trickery that allows me to use one single array. But it's also trickery. You might say, well, okay, I'm trying to use the same array to overwrite. I'm trying to overwrite this array that's supposed to be 2 separate rows, but I'm trying to kind of merge them into one to save space. How does that work? Well, if I'm trying to overwrite this entry, then I need to look at these two perhaps. Then if I try to overwrite this entry, I need to look at these two, and so on. I'm always looking at things to my either the same index or to my left. I will never look at things to the right. Why is that important? So if that's the case, notice that my loop runs backwards instead of forward. And that's very important if you want to do it like this, because if you run the other direction, so if you go this way instead, so you compute this one, it's either based on this one or this one. So you updated this, but remember that updating this is the same array, so you updated this one. So by the time you compute this one, you would have used the wrong entry because this is already updated this is already the value in the next row. Okay, this might be, I don't know how clear that was. This might be too confusing. It's not really that important, to be honest. If you didn't understand any of this, just use the two-dimensional array because it's much less confusing. If you know what you're doing, you can use a one-dimensional array to try to save space, but it doesn't really matter. It doesn't change the complexity at all. Now, there's one other thing that's a little bit maybe requires a little bit of explanation here. I keep a running total of all the numbers that all the package size I've seen. And then when I loop, I only loop from that position on. So what am I saying? So if this is V, and I know that after 3 packages, if I use all 3 packages, I can, this is as much as I can ever reach, right? So maybe my first 3 packages are 1, 3, and 4. Then you know that 8 is the biggest you can ever reach, even though the max is actually 10 to the 5 over here. There's actually no reason to bother computing any of these entries because you know that you can never reach them. So this is just a little bit of optimization to only compute the numbers that actually matter because you know that there's no way you can actually reach them. Anyway, otherwise, you can use the two-dimensional version that I described before in these slides. That would also work. Oh, wait, I haven't shown you this is just a knapsack, right? I haven't shown you what I do with the rest. So I do the knapsack for the hot dogs. I do the knapsack for the buns, okay? And then what do? I just loop through all the possible values of hot dogs and buns that I can buy. If I can make that number of hot dogs, if I can make that number of buns, then I just take the sum of those two, okay? And then my best is just the running minimum, okay? And then at the end, so I set originally the best to be bigger than the total number of packages of both hot dogs and buns. And then if this never happens, then best will still be this, which is bigger than the total number of packages. So then I say impossible. Otherwise, whatever value is stored in there is the answer. Okay, so there's a little bit of maybe, I don't know, implementation mess because of the way I did it to make it a little bit, I guess, less memory hungry, but it doesn't really matter too much. Basically, I'm running knapsack twice. You notice that I just wrote knapsack once and called it twice with different values, one for the hot dogs and one for the buns. And then I just, for each hot dog and each bun value, I just check if you can make that. And if you can make both of those, then that's it. Then you just sum up the packages required to make the hot dogs, that number of hot dogs and that number of buns, and then take the minimum over all possible values. Any questions about this one? Okay. So now, now I said that the last 3 are all graph problems of the same kind. So the question is whether you know this, whether we should have maybe a little refresher. So for for those of you that have taken 3620, how many of you have heard of or seen something called network flow, or some people call maximum flow? And maybe I think I might have talked about this before, once or twice. How many of you heard of this and remember what this is?
I've heard of it only because I was looking it up today, because I was trying to solve those problems. So I figured out that it was network flow. I never really figured out how to implement it.
Okay. Did you guys talk about it in 3620 at all? I don't know.
I don't think so, no.
Okay. Yeah, it's not usually covered in that course, although I know that some instructors sometimes talk about it. Okay, so what is network flow or maximum flow? There's the same problem. Okay, so you have a graph, a directed, so this is important, a directed graph. And you have these nodes, so graph has nodes. And their edges, maybe you have something like this. Okay, on each edge, there's a number, okay? Usually a positive number could be 0, but we don't think that there can be negative numbers. Let me think here. I'm missing numbers. Make this bigger. And then maybe this one would be okay, something like this. And then there are two special nodes. One is called a source and one is called a sink. Now, what are these numbers? So you can imagine that each edge is a water pipe, okay? And this water pipe allows water to flow in the direction that it's indicated by the edge. And the number 5 means that every minute, let's say 5 liters of water can flow through. Okay, so you can imagine that 5 is a sort of wider pipe, and 2, it's much narrower. So every minute, only 2 liters of water can flow through that pipe. So imagine that you have a water tap that comes on at the source, and there's no limit. You can just turn it on as much as you want. Now, if you turn it on as much as you want, so water come into this node, any water that comes into a node must go out. They must all go out. And if you're not the sink, if you're one of these internal nodes, whatever comes in must go out. So if you have 5 units coming in, 5 units must come out. But the 5 units doesn't all have to come out in a certain way. For example, it can be maybe 3 units go this way, and 1 unit go this way, and 1 unit go that way. Right? The 5 unit can be split up somehow. But over here, there's only a length that goes out with capacity 1. So even though there's a length that allows 2 units of flow into this node, it cannot actually accept the 2 units, because if 2 units come in here, only 1 unit can flow out. So there's going to be overflow here. That's not allowed. So this is what is called flow conservation. That means at each node, the flow in equals the flow out. The only place where you don't have flow conservation is at the source and the sink. So source, you're allowed to basically dump in as much as you want, provided that it can come out. I guess actually even the source is the same. If you decide to put 7 in, all 7 must come out. You cannot put in 8, for example. And similarly, if you really take 11 units, 1 from here and 10 from here, then 11 must come out. But there are no edges going out of the source. sorry, no sink edges going out of the sink, and no edges coming into the source. So I guess that I shouldn't be drawing a circle because I didn't mean that there's a separate node. I mean that this thing is called a source. This is just an arrow pointing to the node to mean that this node is the source. So that's why I say that flow conservation doesn't actually happen at the source of the sink because source doesn't have a way in terms of a graph. Similarly, the sink doesn't have a way out. So the idea is, if you turn on this tap at the source as much as you want, and everywhere satisfy this flow conservation, what is the flow that you can come out at the end, right? So you might say, okay, well, maybe here, 5 units can go in here and 2 units can come here, and then 2 units can go this way. So this 2 units can come here, can go follow through, and just keep following. This 2 just take this path, and then you end up here. So you have a 2 unit this way. But what about the 5 units here? Can it make it all the way through? Well, you might say, well, let's push 2 units this way, but that doesn't work because this part you can only take 1. So somehow in this, you can at most push 1 this way. And then you have 4 more that you have to split up. So maybe you split up 3 of them this way, but you push 3 this way and 3 this way, and then 3 this way. But there's already 2, so that's now 3 plus 2, which is still okay. And then maybe you push 1 this way. So maybe you would put 1 this way, and then you push another 1 this way. So this is 3 plus 1 equals to 4. And then this push this way. And then it turns out that you can actually get all 7 units back at the sink, even though it's somehow split up in different ways. So sometimes you cannot always, push as much as you want here and then hope that everything will collect, because sometimes you will have places like this where the number of things that can go in is actually bigger than the number of things that can go out, and then you're kind of limited. So basically, if you imagine that this is all a network of real actual water pipes, and you basically turn on the water as much as it can go, at some point it will just kind of saturate. And that's what's called the maximum flow of a network. Okay? Does that make sense? I mean, I'm not talking to you about how to solve this problem at all. I'm just saying this is what a network flow problem is. Does that make sense?
Yeah, the concept makes sense, yeah.
Okay. All right. So now, I still don't want to talk to you about the algorithms to solve these problems yet. What just happened? Why is, oh, I see, I added the pages out of order. Okay, so network flow. What kind of problems can it solve? Right? Why do we care about network flow? So easiest thing to do, I guess, most obvious thing, I suppose, is have a water network. But this, we usually don't study water networks. Traffic flow. Okay, so maybe you have a 2-lane highway, so you can say, well, 2-lane highway, you can have this many cars per minute driving through and not have congestion. And then you have intersections, and then so on and so forth. You can have a street map with basically the capacity of each road, and then you can say, what is the maximum number of cars that can go from one place to and ending at another place without causing any congestion, right? Without saturating any particular, I shouldn't use the word saturate, without overflowing any particular road. And so traffic flow for roads and cars, I guess. You can also use it to model traffic flow over networks, right? So this could be bandwidth of particular internet links, let's say, the network cables or whatever you want to call it, or it doesn't have to be cables, it can even be just some kind of wireless net channels. But anyway, you can have traffic flow And you might know that when you use the internet, for example, it breaks things up into packets, and each packet can be routed independently of each other. And then at the end, somehow everything gets assembled, right? So this, how much traffic can you send from one place to another, given the bandwidth of each link, if you're allowed to split things up. So those are sort of the more, I guess, obvious kind of applications. And then another class of problems that are that are maybe a little bit less obvious, what we call some kind of an assignment type of problems. So you have typically multiple type of things. So for example, could be workers was one type, and then jobs, for example. And then you need to assign certain one type of things to another with some constraints. So what do I mean by that? So for example, maybe that you say, give certain jobs to workers, right? So you have 10 different jobs. You have a bunch of workers. Which workers get what jobs? What are the constraints? It could be that some workers can't do some jobs. So maybe not everybody can do everything. Maybe some jobs require skills that some workers don't have. So there's some constraints. There can also be some other constraints, like maybe at most, some number of jobs per person. So maybe you don't want to overwork people. You want to make sure that nobody gets more than 2 jobs, 3 jobs, maybe. Okay. Or it could be other kind of constraints. Maybe you can have multiple people working on the same job. So you can have at most K people per job. And maybe each job is done by more than one person. So there are many different kind of constraints, and they can be all kind of modeled. Okay, so let's think about this situation. So you have, let's say, N workers, M jobs, and let's say that you have at most K jobs per person. So no one can take more than K jobs, and at most L jobs, no, at most L person per job. I guess it's per, not persons, people. Well, it doesn't matter. We're computer scientists. We don't know how to spell. Okay, so let's say that these are the constraints. So how do I make this in a network flow? The idea is that we're going to give each person some kind of, I don't know, tokens, if you want to call it. And we're going to have workers. So we're going to have nodes that represent workers, the N workers. You're going to have jobs, the M nodes that represent the jobs. Okay. Now, every time a worker can do a job, so if this worker can do this job, I'm going to draw an arrow saying that I am allowed to use this edge. Maybe I'm not, maybe this worker doesn't know how to do job 2. So you can just draw things like this. Basically, you only draw an edge with capacity 1 if that worker can do that job. And if they cannot do a certain job, you don't draw the edge. Okay. Now, you're going to give each worker you're going to give each worker K tokens. Okay, because they're allowed to do at most K jobs. Every time they decide to do a job, they have to pass one token to that job. Okay, so this is kind of like water flowing, I suppose. But we're talking about these, instead of water, this is the tokens. Every time the worker wants to do a job, they have to pay the token to the job. Now, on the other side, each job, when somebody does a job, then it's going to collect a token from somebody. And then it's going to connect to, so this is a sink and this is the source. And it's going to collect, each job can collect at most L different tokens, right? You're not allowed to collect more than L. So the capacity of this link is L. And this is the network that is used to do this assignment problem in terms of maximum flow. So what I'm flowing is some kind of tokens that get passed from one type of thing, in this case the workers, to another when they get assigned. Okay. Now, for example, here, if this worker gets both jobs, then he'll take this K tokens, pass one to this job, pass one to the other job, and pass the other remaining tokens to whatever jobs he can get assigned to. And then this job will make sure that it cannot collect more than L tokens. Okay, because if it collects more than L tokens, then too many people are doing this job. And then if you run maximum flow and just see, basically just let this run, then this will basically try to get as many jobs assigned as possible, possibly multiple times. Okay, but it's still possible, but the way that this is set up, I'm trying to maximize the number of tokens collected at the end. And it's possible that if the best answer is like L, it's possible that one job get L person and no other job gets anybody, instead of versus L jobs each getting one person. Both of them are equally good because the total number of tokens collected at the end is the same. Okay, so I'm trying to maximize the number of tokens that are either sent out at the beginning, collected at the end. But basically, what I want to say is, whenever you have assignment type of problems, it's common that you have a certain group of nodes for one type of thing, another group of nodes for the other type of things. You connect them in this way from one type to the other and never backwards. You connect one side to the source and give them some kind of tokens that they can pass around when they get assigned stuff. And then the other parts would collect these tokens and pass them to the sink. Okay, so if you recognize that you have either a network flow or an assignment problem, then I would say that 80% of the battle is to figure out how you build this graph. Now, why do I say 80% of the battle is how to build this graph? It's not that you don't have to solve the actual network flow problem, but because either you know the algorithm already and can write this code by heart, or you just go to my code library and discover that we have network flow algorithm. And if I look at my solution, the first thing that I do is I just basically paste the network flow from my code library. So there's quite a bit of code here. I'm not asking you to remember all of it, but basically this is the main function to call. You set up a graph, you build a graph, you add the edges somehow, you call network flow, and then that's kind of the end of the problem, almost the end of the problem. So 80% of the battle is to try to figure out what graph to build. You call network flow, and then the other 20% is to figure out how you read the output of the network flow. So I guess I will start with the easier one. and then kind of explain to you how this graph is done. Okay, so the first problem, maze movement. Your boss gave you the task of creating walking maze, blah, blah, blah. Okay, after your boss is interested in making money on this venture, the faster people can move through, the more paying customers you can handle. A maze is a set of number of rooms and passages connecting the rooms. The maze only entrance is at the lowest number room. So in this case, 4, 6, 9, and 8. Entrance is at 4, and the only exit is at 9. So this is the source, this is the sink. Each passage is a limit on the number of people that can pass through at a time. Then they give some funny way of computing this capacity, right? So for 2 rooms number X and Y, if X and Y have a common factor greater than 1, there's a passage between X and Y. And the largest common factor P is the number of people per minute that can walk from X to Y. So 6 and 9, the largest common factor is 3. So the capacity of that link is 3. And in this case, it's both directions. Okay. So what's going on here? This is a bidirectional link, but I told you that this is a directed graph. So what you have to do is actually just draw a link in both directions. Okay. And then basically, once they set up this capacity, the question is, what is the largest number of people per minute that can go from the source to the sink? So that's exactly network flow. So they give you a more complicated graph. It doesn't really matter. So the input is the number of rooms and then the labels of the room. So here, I'll just quickly show you my submission. Okay, so I include the standard stuff. Then the next thing I did, I just pasted exactly the network flow code in my code library. I didn't do any changes. Okay, so there's a function called network flow. It takes in something called graph object, the source and the sink. So in many algorithms, in many books, S is used for source and T is used for sink. I don't really know why, but that's the standard labeling. And then a graph is this class, well, kind of like a class. The way they initialize it is just graph with the number of nodes. There's a destructor. And then you just say, if you want to add an edge from U to V with some capacity, you just call add edge. That's it. There is no check on duplicate edge, so it's possible to add multiple edges. And if you add multiple edges, it actually does mean that you have multiple pipes, each that can pass whatever capacity you say. Okay, so how does it work? I read a number of rooms, I read in all the room numbers. I sort them from smallest to largest because I was told that smallest is the source and the largest is the sink. I build a graph of this size, and then I just look at all possible pairs of rooms, compute the GCD. If the GC is greater than 1, then I add an edge in both directions of that capacity. And GCD, of course, is just a Euclidean algorithm. Where do I have it? Where's GCD? I'm sure I have GCD somewhere, no? Where is GCD? Did I miss it? GCD. Wait, how does this work? Is GCD a function in G++?
Yeah, but I thought you had to have like 2 underscores for it to work. So I've been using 2 underscores GCD and it works. I think you include algorithm or something.
Oh, it's in C++ 17. Okay. This is new. Right. Okay. Yeah, okay. At some point it didn't work, but now it works. because it's in C++ 17. Okay. So I was smarter than I thought. Okay, so I computed GCD and so on. And then once I build this graph, then I just call network flow from source to sink, and whatever that flow is, that's the answer. So this is basically a very, very simple application of network flow, right? This is almost as standard as it gets. You know, analyzing traffic flow, they pretty much tell you how to build a graph. You build it, you call the network flow, you're done. That's it. Any questions? Okay, now I'm kind of going backwards here. So I will look at counseling because I think the description is shorter. Okay, so each resident of a particular town is a member of 0 or more clubs and also a member of exactly one political party. Okay, so everybody has a political party and they might belong to 0 or more clubs. Now, the town council is going to form, and each club wants to have 1 member. Okay, so every club wants to send 1 member to the council. But they want to make sure that the number of council members belonging to any given party, to any given political party, does not equal or exceed half the membership of that council. So basically they want to, each club wants to send a representative to council, but they don't want it all to be a certain, they don't want too many people from the same political party. The same person may not represent 2 clubs. Okay, so even though a person might belong to multiple clubs, they can only represent 1 club. And so that is, there must be a one-to-one relationship between clubs and council members. Your job is to select the council members subject to this constraint. Okay, so that's the question. First line of input, there will be T, which is up to 12, number of cases. Okay, so that number of cases doesn't matter, you just do it T times. So each of the t-test cases begins to align with the number of residents n. So there are up to 1,000 residents. The next n lines each contain the residents, the political party, everybody has a political party, the number of clubs he belongs to, and the names of all the clubs. Each resident appears exactly 1 line. So here, 2 cases. The first case, 4 people. First person is Fred, belongs to a dinosaur political party, belongs to 2 clubs, Jets and Jetsons. The second person, John, he's in the rhinoceros parties, belongs to 2 clubs again, Jets and Rockets. Mary belongs to rhinoceros parties, belongs to Jets and Rockets. And Ruth is in the platypus party, belongs only to 1 club. And then the output is each line should name a council member followed by the club represented by member. If there are several answers, any will do. If no council can be formed, print impossible. So here, it turns out one solution is that Fred represent Jetsons, John represent Jets, Ruth represent Rockets. And then this actually is exactly the same case, so you expect exactly the same answer, I guess. And then here, the second example, you have 1 person, Fred, dinosaur club, a dinosaur party, we don't do 2. So it's impossible in multiple ways. First, there's no way you can have 2 club members. Now basically you have 2 clubs, so you need 2 members on a council, but there's only 1 person, so that fails automatically. Also, there's only 1 political party, so of course it's going to be majority if you actually choose all of them. Anyway, so there we are. So this one is a little bit more complicated because before we were talking about, well, there are multiple, that you assign one type of thing to another type, but actually here we have 3 types of things here. We have person, we have political party, and we have the clubs. I guess I should use singular. So we have club. You have 3 different types of things going on here, and you have to kind of assign, well, what are we assigning? Are we assigning club? We're assigning club to person, yes? Because we're trying to say that each club is going to pick a person. And a person, when you pick a person, automatically each person comes to the political party. And you want to make sure that each party doesn't have too many. And here, you want each club to be exactly 1 representative. So if you're kind of drawing this, you're kind of saying, okay, maybe club connects to person. So basically you give each club a token. They can pass this token to the person that represent that club. And that person will pass his token to the political party that they belong to. And then the party would collect all these tokens and make sure that they don't collect too many tokens. And that's basically the idea. Okay. So what we're going to do is we're going to have a bunch of nodes, which are the clubs. And the source node would basically distribute a token to each club. And then basically every club, all its members, okay, maybe it has 3 members. This would basically say the token that's received by the club can decide which person to pick. Okay. And whichever person is picked by the club will give that token to that person as the representative. So basically, every club would have an edge to all its members, each with exactly capacity 1. Then you have the political parties. You have all these political parties, and all its members. So maybe a political party will have a bunch of members. Oops, sorry, no person can have more than 1 political party. Would also have capacity 1, meaning that whatever token this person gets from the club, he will pass it on to the party. Now, it's possible that a person belongs to multiple clubs. Okay, maybe this person belongs to 2 different clubs. But there's only one token that can be passed. That means that this person cannot collect 2 tokens. He can only represent 1 club. Okay, so this is how you make sure that every person can only represent 1 club. This one makes sure that every club can only elect 1 person. This part makes sure that every person can only represent 1 club. And then every party is going to collect all the tokens from all the people that are in the council. And this has to be, I'll just write it in quotes. The capacity has to be half minus 1, because they tell you that the number of people in each party, the number of people for each party on this council cannot be half or more. So you basically have to figure out what half is and then make it 1 less, and that's the capacity. And that makes sure that no party has too many representatives. Does that make sense? Any questions before I move on to the next part? It is kind of complicated, but the structure is similar in that every type of things that are in your problem has a group of nodes. Okay. Now, the problem, there are other problems that you have to worry about. The other problem that you have to worry about is when I make the graph in my code, I just have to tell the program that I have n nodes. Well, what is n? Right? So I have to know the number of clubs plus the number of people plus the number of party plus 2, because I have to worry about the source and the sink. So I have to, when I read the input, I have to figure out how many unique clubs there are, how many unique people there are, how many unique party there are. Or I can just go for the absolute worst case and say, I think the number of people is at most 100. Is that true? I don't remember. Yeah, at 1,000. Okay, 1,000. So at most 1,000. At most 1,000 people. So I can go for that. I can just say that most 1,000. The number of parties is also at most 1,000, because in the worst case, everybody belongs to a different party. But that probably is not, probably you have multiple people in the same party, but in the worst case, it's at most 1,000. What about number of clubs? In the absolute worst case, every person has exactly 110 different clubs. So it looks kind of big, sorry. But it doesn't really matter, it's just a number. So you basically say that the number of nodes is this plus this plus this plus the source and the sink plus 2. So this plus this plus this plus 2, that's the number of nodes when you build this graph. You can be more precise if you wish. You can actually read the inputs, remember everything, and say, aha, I only have 5 people. So I'm only going to use 5 nodes over here instead of 1,000. You can do that. Or you can just say use 1,000 and then only bother to use the first 5 nodes. And then the rest you don't even bother connecting. That's fine too. Okay, so I think it's actually easier to just use the maximum. Then you have the issue, whatever n is, the node index is going to be between it's going to be between 0 to n minus 1, where n is this big number. How do you make these, how do you label all these nodes to 0 to n minus 1? Right, so you have to come up with a numbering scheme. So for example, maybe you say, this is source is 0, sink is 1, and then you start counting, I don't know, maybe person is 2, 3, 4, up to, if you use 1,000 as the maximum, maybe it's, what is it? If you use 1,000 as the maximum, it's like 1,001. And then maybe party, you start from 1,002, 1,003, and up to 2,001. And then the clubs you go from 2002 and up. Okay? It doesn't really matter how you label them. What I wrote down is just one particular way. It makes no difference how you label them at all, as long as you can figure it out, right? As long as you can keep track of things. Also, there are other issues that the problem doesn't tell you person 1, person 2, person 3. They actually give you a string. So you have to remember that you have to somehow map this word is number 1, this word is number 2, and so on. And this is a general indexing problem, translating names, strings from names from strings to numerical labels. So if you can get all of that figured out, then you can build a graph. Of course, you also have one thing that I didn't mention is what is half minus 1. Well, if the total number of clubs, right, each club is going to send one representative. Well, if you divide by 2, that's half. But then you have this problem. Anytime you divide by 2, you have to worry. Are you dividing by 2 from something that's odd or something that's even? Because if you take this, if number of clubs is it's even, dividing by 2 is exactly half, which is not good, so you need to subtract 1. But if number of clubs is odd, when you divide by 2, if you use the C++ divide, then you already lost the 1/2. So it turns out that if num clubs is odd, then you just need to divide by 2. So you can kind of, I don't know, mess about trying to figure out how to write the half minus 1 when it's num clubs is even or num clubs is odd. You can have if statement, if it's even, do something, if it's odd, do something. Or you can just kind of eventually figure out that you can do it all in one go by writing -1/2. And it will turn out whether it's even or odd. This will give you the number that is just smaller than half. Okay, I write half -1 in double quotes because when number of cups is odd, half of something that's odd actually has fractions. So it's not exactly -1. It's kind of like -0.5. That's why I put things in quotes. So it's all kind of complicated. But before I show you the code, are there any questions on this graph, the way that this graph is set up? The most important thing is to remember that you want to have a group of vertices for each type of things. How do you order them? Which one connects to what? Well, then you have to look at the problem and say, well, club assigns a person belongs to a party. And then usually the source and the sink, it connects to the problem here in the way that, you know, each club has to send one representative. So you give them all one vote or one token. And then each party can have at most a certain number of representatives. So you make sure that each party collects a certain amount. You can actually turn all of these arrows backwards, call this the source and call this the sink, and exactly the same problem, exactly the same network flow. So you can choose to send things from party to club. It's the same thing. So just to show you the code. So again, the code, I start with all this network flow code that I just copy. Now this is just a general function that basically have a map that converts the name in as a string to a number. And then basically I'd say, well, have I seen this before? If I have not seen it before, if I have not seen this this word in my map before, then I add a new entry. So what would my map look like? My map would look like at some point, maybe it will say, you know, string 1, it's index 0. So there'll be name and index. So there's a key and a value. And then there's another string and the index is 1, and another string, the index is 2. I have a map like this. So let's just say that this is all I have. And now somebody asked me, what is the index of S2? Well, I look up, it's there. So the entry is already there. I just return it. End of story. No problem. But what if somebody asked me, what is S4? And I go and look in my map, S4 is not there. So what should I do? What I want to do is to make it this. Okay, so how do I make sure that I get the right index? So what do I do? The size right now of this map is 3. There are 3 entries. And this size is exactly what needs to go into the next entry. So I look at the size, m.size. I assign it to some temporary. Okay, forget about the base for now. And then I assign it to the entry for that string. So I put S like this. Okay, so that's how this code works if you ignore the space. The base is just an offset. Okay, so I'll tell you why. So basically, why do I have this offset? Because I told you that maybe all the people will be from 2 to n plus 1. So instead of starting at 0, I want to start at 2. So if I'm looking at people, then I add base to be 2. So everybody will start counting at 2. Now, I want to show you something that is often done incorrectly. And it's this piece of code. So again, forget about the fact that there's a base. So I wrote it like this. I assign m.size to be t, and then I assign m bracket s to be t. And a lot of times I'll see people write this instead. Right? Because it seems kind of silly. Yeah, I take this, assign to T, and then I take T and assign to this. So why not just write this? So anybody wants to tell me if this is correct? Well, I guess I already told you this is not correct. Does anybody understand why this is not the way to do this? This is, if you can answer this question in a technical interview, you're probably going to be hired. You'll probably impress a lot of people. What is the difference between this and writing it in this way? It looks almost the same. Forget about the return. The return is a red herring. But the idea is, why did I have to break this assignment into assigning a temporary and then putting in the M bracket S? Why don't I just write it all in one go?
Is it because when you add like S to the map, that increases the size by 1?
Okay, that's a good start. Okay, so if you do M bracket S, because S is not, you only get to this line if S is not part of the map. So as soon as you write M bracket S, that will create a new entry in the map. And when you create a new entry in the map, then this will get bigger. So you might, so if your original map was like this, then the new entry you get may be 4. Is that what you're thinking?
Yeah.
Okay. Okay, before I go on, does anybody understand why I write this down and say that you get 4? Is there any question why this is 4? And so you miss 3. When you do it this way, then you don't have this problem, because this line cannot possibly increase the size of M. And then down here, you can increase the size, but you already got the value of size, so you won't get affected. Does that make sense?
Wait, the size went to 4?
Yeah, well, if you use this, it'll be 3.
Okay, yeah.
Yeah, if you use this one, now, okay, so whatever you answered, you have not impressed me yet. You have impressed me somewhat, but you have not, I'm not fully impressed yet. And then the next part, it's this. I said many people will write this, and many people, that program will be correct. They run it, it will work. They never think about it ever again. But some people,
Are you supposed to use size of?
no, actually, size of is a different thing. Okay, so the digression. Okay, so digression. Size of bracket something. It's a C++ primitive, I suppose you call it, that determines the amount of memory that is used to hold something. So, for example, if you have size of int, it will tell you on our machines 32. If you have a size of A, where A is an array, then it will tell you basically how many bytes. Okay, so it's how many bytes, not how many elements. This is how many elements. But there's actually more to this. If you're putting any complicated data type like an object, then it actually will only give you the size of the structure that holds the object. So what is the difference? The difference is probably inside a map, it only holds a pointer to the root of a binary tree and a few other things. So the size of will only tell you the sum of all those data fields. But if you have a linked data structure, it will not tell you the size of the whole thing. It will just tell you the size of the top level stuff that is stored in the structure. Okay. But anyway, size of it is sort of always expressed in terms of number of bytes, and this is in terms of number of elements in whatever data structure you're using. Okay, so why do I say that sometimes this is actually okay and sometimes this is not okay? And this is going to be, yeah, something that is very deep in C++. So what is going on? This is a function call, right? You have to call a function to find the size, that's the member function from the map class. What is not so, I guess, what is not so obvious is that this square bracket is also a function call. It's an operator overload. So it's actually also a member function in the map class, correct?
That makes sense.
Okay. Now, one thing that it's in C++ is that if you have f, let's say you have a function that calls two different things, and there's some expression one, you have to do something to compute this, you have to do something to compute this. So before you call f, the compiler first have to compute, or the program first have to compute what is the value of expression one. It has to compute what is the value of expression two. And when it knows both values, then it can call function with the two parameters. So far, so good. Now, in C++ standard, there is absolutely no requirement that the expressions 1 and 2 have to be computed from left to right. The compiler can choose to compute these two expressions, or in general, if you have multiple parameters, it can choose to compute multiple parameters in whatever order it pleases. So it can decide to compute expression 1 and expression 2, which is maybe what people expect. It can also compute expression 2 first, then compute expression 1. And if you really have fancy hardware and you can do things in parallel, it might even decide to do both at the same time. Okay? All of those are legal C++ compilation. And so if your expressions here and here, somehow if your expression 1 and expression 2 has side effects, where expression 2 depends on the side effect of expression 1 or vice versa, then that code is unpredictable. It may or may not work depending on how it's compiled. And this is exactly the same thing, because you can imagine a function with two expressions, and the only thing it does, the definition of this function is just say expression 1 equals expression 2. You can think of an assignment as sort of like a function with two parameters. So there's one parameter here, there's one parameter here. If you execute this function call first, then you assign to it, then you execute this one, then everything is fine because you haven't increased the size of this map first. But if you do it the other way around, you're toast. And there's no way you can force the order of evaluation, which one comes first in a single statement. The compiler is free to choose whatever order it pleases. Okay, and then the reason why is because sometimes the compiler can realize if it does things in certain order, it can maybe reuse some computation and save some time or space or whatever it is. Okay, so there's no way you can force C++ to execute, let's say, the right-hand side first before you execute the left side, or vice versa. The only way you can force it is by breaking in two statements, because when you see a semicolon, C++ says, okay, you told me you must do this before you do the next thing. And that's when you force. Okay, so that's just an aside, I guess, but a fairly important aside is that when you write a statement when you have multiple parameters. I know that maybe this assignment operator doesn't look like there are multiple multiple things to multiple parameters to evaluate, but in fact there are. There's the left-hand side and there's the right-hand side. Each one of them requires a function call. There is absolutely no way you can force one to be executed before the other. Compiler is free to choose whichever one it wants. And moreover, even if you use the same compiler, same machine, depending on compiler setting, it may decide to change the order. But if you decide to optimize versus not optimize, it might decide to switch the order on you. So if you write code like this, it may work on some compiler setting, and then you just turn on optimization, it doesn't work anymore, and then you'll be spending forever trying to debug this damn thing. So basically what I'm saying is code like this, it's unpredictable, don't do it. So if somebody asks you this question on job interview and you know the answer, you will probably be the 5% of people in the world that will answer this correctly. There are not many people that can that know this. Of course, if somebody explained it to you, you probably know it, but to be able to recognize it, it's pretty hard. All right, anyway, that was a digression. We're still talking about how to map strings names to numbers. Okay, so here we are. We have a map, one map for the people, one map for the party, one map for the clubs. And then I remember the names of the people because I have to print them out at some point. Okay, so the graph, I basically use 0 to 1 as source and sink. Starting from 2 to n plus 1, I used it for people. Then n plus 2 to 2n plus 1 is the party. And then 2n plus 2 and on are the clubs. It doesn't really matter what you choose as long as you keep it clear. Right? You just make sure that you don't screw up. Okay, what do? I read the n people. So for each person, I read the person, I read the party, I read the number of clubs, and then for each club, I read the club. Now, what am I doing here? I figure out what is the ID of the person. I figure out what is the ID of the party, and I add in the offset because I start at 2 here for people, start at n plus 2 for party, so I add in this offset. And I add an edge from the person to the party with capacity 1. Okay, so what was it? People, party, capacity 1. So that's what that is. Then for each club, I find the index of the club, and I add an edge from the club to the person. So every club that a person belongs to, I add an edge from that club to that person. Okay, this is just like what I told you. And then what do I do here? For each club, so this is a map, so all the names of clubs that I collected. For each club, so this is name and this is index. I set from source to the club 1. So this is my source to each club. I give them 1 token to choose a representative. And then I figure out what half is. I guess it's half minus 1, but I just call it half. And then for each party, I send an edge from a party to the sink. Every party is going to have this half. So after all of this, I build a graph. I call network flow. And then the maximum flow would be basically the best case scenario is every club can assign somebody. But if every club assigns somebody, I would have some party that has too many representatives. So maybe that's not possible. Maybe the maximum flow actually was less than the number of clubs. In that case, that means not every club can choose a representative, and then it's impossible. So I look at the flow. If the flow is not the size of the number of clubs, then it's impossible. So that's that part. That's the impossible part. But if it's possible, then now I have to somehow recover. Okay, somehow recover the actual assignments. So what I have to do is I have to look at the network flow. This is something I haven't talked about yet. But the network flow code would not just tell me what is the maximum flow, but also how much flow is going through each edge, right? So maybe in the maximum flow, this edge would have 0, and this edge would be 1, and this edge would be 0 because this person can only have one edge, one unit going out. So not all the 3 edges can have flow. So maybe this is the only edge that has 1. So what I'm going to do to figure out which, for each club, who they chose, well, I basically look at all these edges that goes from clubs to people and see which one actually has a flow of 1. And in this case, actually non-zero flow. So there's a little bit of magic going on here, but basically I just go through, for each club, I go through all the edges. So go through all the edges from that club. And then if this is real, it's a little bit strange, but basically, if you want to know what the flow is for that edge, first you have to make sure that this is true. So somehow I have real edge, and I guess you can call it not real edge. So if the edge is real and the value, the flow that sends to that edge is greater than 0, in this case, it's always going to be 1. But in other problems where the capacity is not 1, then if the capacity is 10, for example, the flow might be something small. So it might be something bigger. But anyway, if the flow is bigger than 0, that means this club chose that person. So then I basically print the person's name and the club name. So that's how I recover the actual name of the people and the club that they represent. Okay, so that's this is probably one of the more complicated things for network flow. And well, you should probably look into this and possibly do it. As I said, I usually this is one of the standard problems I ask people to do in 3200 as a network flow problem. There are many other ways you can do network flow, of course, but this is all kind of one of the most complicated ones that you'll see. Any questions? Okay. So now, what do I want to do? I want to go to this last one. Okay. Look, this is apparently a high school programming contest. When I was in high school, I didn't even know what a graph is, let alone network flow. So I'm not completely sure what kind of high school students these are. Anyway, so you have resident advisors, the student leaders that are responsible for helping freshmen transition smoothly, blah, blah, blah. Okay, you're trying to design a system to assist them in the process of scheduling RAs to be on duty every month. On each day, there are exactly 2 RAs on duty. Each RA is available only on specific days and can only be scheduled then. Before the end of each month, each RA submits a list of days with their availability to Mr. Fredo. Your goal is to help them write a program that will take a list of RAs and their availabilities and assign 2 RAs on duty each day. While there's no limits for how many days each RA can be on duty, Mr. Fredo wants to reduce unfairness by limiting the imbalance between the number of days each RA is assigned. Toward that goal, your program needs to minimize the maximum number of days to which any RAs may be assigned. Okay. So there's a sort of slight complication with this minimizing number of days, but let's not worry about this. for now. So you have RAs and you have days. You need to assign RAs to days, 2 RAs per day. Well, this is a classic thing, right? You have a bunch of RAs, you have a bunch of days, right? You connect an edge if the RA says that they can work on that day, and you give them 1 token. Okay, and then how many tokens is each day going to collect? 2, because each day needs 2 RAs. The question, of course, is then from the source, how many tokens do you send to each RA? Because the number of tokens you give them, it's basically the number of times each RA, the number of days each RA can work. And you want to minimize this. So you want to give each RA K tokens. K means that each RA can work K day, at most K days per RA. But you have this complication that you want to minimize. Okay. So how are we going to do this? Well, if we don't have this minimized K, if somebody just told you K, whatever K is, everybody can work at most 5 days. So then you just go and write 5 here, you run network flow, and if the total number of things that you collect, if the maximum flow is exactly 2 times the number of days, then you're done, because that means that every day has exactly 2 RAs. All the other constraints are satisfied, so you know that you can do it. But what if you allow everybody 5 days to work, and when you run this, the maximum flow is less than 2 times the number of days? Well, if that's true, then it means that some RA has to work more than 5 days. So then maybe you try something bigger. Maybe you try 6. Maybe you try 6 and maybe it works. Maybe it doesn't work. If it works, you know that 5 didn't work and 6 works. So you know that 6 is the smallest K that works. If it doesn't work, you try 7. You try 8. So what you can do, if you want, is actually just try K from 1, 2, 3, and up, until the first time where the maximum flow is 2 times the number of days, and then you know that works. And then once you have a maximum flow that works, you can read off the actual flow assignment to figure which edge has flow, to figure out which RA is assigned to what day. You can also use binary search. That also works. You don't have to do a linear search on K. You can actually binary search K. But in this case, it turns out that it's not necessary, because the problem is small enough. So, I mean, I can show you the code, but really it's not really that interesting. I read in the name of the person, I read in the number of days they can work. I have a vector for each person, which days they can work. And then I just basically try for every possible capacity, the K that I drew in my slides, call this network flow. So I build a graph. So again, I make sure I remember what my node indices are for each type of things. So this is, how did I do it? Oh, I actually go backwards. I draw the graph in the opposite direction of what I drew on the whiteboard. Doesn't really matter. So here, every RA is sent to the sink with 1 token. Then every day gets 2 tokens that it can give to the 2 RAs, and then I add an edge from a day to a person if it can work that day. Then I call network flow. If the flow is exact, if it's not the 2 times the number of days, that means I can't do it. Otherwise, I can do it, and then just have to recover the actual assignment. The reason why I did the other way is because I have to, the output, I have to say for each day who are the people. So it's easier if my address goes from day to people. If I go from people to day, then I would be able to say for each person which days do they work, which is a little bit harder for me to assemble this output. So that's why I did it backwards. But in terms of just trying to find an assignment that works, it doesn't really matter which way you do it. So I think I would say that the most important part is to understand how to set up these network flow graphs, and then how to transform your problem into a network flow. And then, of course, once you know how to build this graph, then you have to call the network flow. That's the easy part. And then if you need to actually recover the assignments, then you need a little bit more work to figure out how to read this assignments from the network flow. So anyway, I covered 3 different network flow problems. This is definitely not the only types of network flow there are, but certainly there's a starting set of problems, assignment type of problems where you have different types of things that you're trying to associate one type to another type. It's a really, really common way of using network flow. Okay, and looking at many of these problems will definitely be useful if you can practice these things. As usual, all of these code is in my GitHub. So if you want to refer to it later, if this is unclear, you want to see what I did, you can always go to my GitHub directory and look at my submission. Okay. So if you're thinking about taking 3200, for sure you should do some of this, especially counseling. I'm not saying that I will use that question again, for sure, but it is one that I've used often in the previous term. So if I don't use that one, probably I'll use something similar anyway. Okay. Okay, I think that's the end of this week. Any questions? Let me stop the recording, stop the share, stop the